Dear students, welcome back. So now in this my second lecture, I'm going to take the electrical conductivity due to the intrinsic semiconductor, and before that we'll be taking up the Fermi energy, and that also in case of the intrinsic semiconductor. Then later on we'll see the Fermi energy in case of the extrinsic semiconductor as well. So Fermi energy is just like your center of mass. Just you can say as the center of mass behave exactly in the similar way, Fermi energy also behave. How does the center of mass behave? That if let us suppose if you have taken any rod, let us suppose this is a type of the rod you have taken, and if it is uniformly made, then the center of mass will be exactly at the center of the rod. But on one side, if you are going to load this, if you have started loading over there, then center of mass will be shifting, and it will be shifting towards in this way. And here if you are going to put your finger at this point, then you can balance the rod on your finger. So similarly you have the Fermi energy. So Fermi energy, if it, let us suppose if it is a uniform rod, then the Fermi energy will be exactly in between. So here what we are going to do is we are going to instead of this rod, we are going to take the valence band and the conduction band. And we know in case of the intrinsic semiconductor, the electrons are in the conduction band, and the holes are in the valence band. Now since we know the number of the electrons and number of the holes will be exactly equal, right, in case of the intrinsic semiconductor, so what we expect that the Fermi energy will be lying in between your energy gap, right, because at the zero Kelvin you have what you have, that the conductivity is 0. So as you are going to increase the temperature, the electrons break, and electron will jump over your Fermi energy and it will go to your conduction band. So as many number of the electrons is jumping into the conduction band, that many number of the holes is being created in the valence band, and therefore the energy that is the Fermi energy should be lying exactly between the valence band and the conduction band. That is exactly in between your between the energy gap. So how it comes? Let us see in with the mathematical expression, with the help of the mathematical expression. So this is the Fermi level in intrinsic semiconductor. So we know for an intrinsic semiconductor, every time an electron moves from the valence band to the conduction band, it leaves a holes behind the valence band. The density of the electrons in the conduction band and the density of the holes in your valence band are always going to be equal, right? This is the basic concept that we understand in case of the intrinsic semiconductor. Mathematically, we have seen that the electron density or the hole density in the conduction band and the valence band is given by Nc exponential EF minus EC upon kVt, and similarly for the holes it is given by Nv exponential EV minus EF upon kVt. And now we know the number of the electrons in the conduction band is going to be number of the holes in the valence band. So what I have done, these two I have equated and I have made it equal. So what we can say here, Nc is the effective density of the state in the conduction band, Nv is the effective density of the states in the valence band, and Ef is the Fermi energy, Ec is the conduction band age, and Ev is the valence band age, Kb is the Boltzmann constant, and T is the temperature in Kelvin. And about all these nomenclature we had already seen while we had seen this expression. That let us suppose this is your expression, your equation number 1. So as we are taking up this equation, we had already seen all these things. All right, now what we have to do is we are just going to rearrange this equation number 1 and so therefore what we are going to do is we are going to take the ratio of Nc and Nv, and by taking the ratio of Nc and Nv, we want to show that the Fermi energy will be lying between the conduction band and the valence band. So this is what I am going to do. So just you rearrange your this equation. So what I have done, Nv upon Nc. So this Nc I have brought on the right hand side. So Nv upon Nc. So this equation, that this part will come on the left hand side. So you bring this on the left hand side and then just you rearrange. So what we can say, this will equal to your exponential 2EF minus EC minus EV upon kVt. So just a small simplification you can do. What we have done, that this we have divided NV upon NC I have taken. So this will become exponential EF minus EC upon kVt whole upon exponential EV minus EF upon kVt, right? And just you take up some of the expression above, right, and rearrange this, you will be getting this equation. Now what you do, let's take the log on both the side, that is a natural log we'll be taking. So if you are going to take the natural log, so on the right hand side here we'll have the ln, and this exponential will go out, so it will come something like this. So right hand side, as you can see, you are getting the ln, and from the left hand side the exponential has gone, right? So this is your the ratio of NV upon NC. Now we know the NV and NC will be equal because the energy density for the electrons is equal to the energy density for your holes. All these things are equal. So NV and NC are equal in case of the intrinsic semiconductor. So this is what we are going to put over here, right? That I will be taking later on. So first what I have done, just I have rearranged this and I have taken the value of EF. So what is the value of EF? So EF I have left on the left hand side, and all other factors I have taken on the right hand side. So what we are getting, EC plus EV by 2 plus kVt upon 2, because as you can see here the kVt is there, right? So kVt will go there and it will get multiplied, and this 2 kVt by 2, this is your 2 which has come over here, log NV upon NC. Now as I told you, NV and NC are equal. So if you are going to take the log of this, so ln is equal to 1, right, in this case, and the moment you are going to say this value of 1, so this entire value is coming out to be 0, right? Ln of 1 is going to be 0, so this value will be coming out to be 0. So then what we are getting, Fermi energy we are getting is equal to EC plus EV by 2. That is, Fermi energy is exactly lying between the conduction band and valence band. Let us try to understand with this given figures. So now, as we know, as we are increasing the temperature, so this being shown with the increase of the temperature. So with the increase of the temperature, the Fermi energy is moving towards your conduction band, right? Now at any time as we know, the number of the holes, so this is the number of the holes that we have taken, is always going to be equal to the number of your electrons in the conduction band, right? And this is the reference level for your conduction band, and this is the reference level of your valence band. So what we are finding, the Fermi energy is lying exactly in between the conduction band and valence band. So what we understand, that in case of intrinsic semiconductor, the conduction band, the Fermi energy will always be between the conduction band and valence band, right? Now let us start the electrical conductivity in intrinsic semiconductor. So here let us suppose we have taken any specimen of the semiconductor as we have seen here, and we have applied a certain potential through this, that is, we are going to apply the electric field, right? And then what is happening with the thermal energy if we have given? So the covalent bond has broken and the electrons and holes start moving. We have already seen the electrons and holes will be moving in the opposite direction, right? Because of the hopping of the electrons. So here what we are saying, the electrons are moving in this direction. This is the direction of movement of the electrons, and this is the direction of the movement of the holes. Now naturally, the total electrical conductivity that we are going to get is due to the sum of the conductivity due to the electrons and due to the holes. It will be sum of both. So this is what we are going to look into in this equation and in this section, and that we are going to do it mathematically. So what we are saying, in an intrinsic semiconductor, even at room temperature, holes electron pairs are created. So naturally at absolute zero, no covalent bond has been broken, but as you are increasing the temperature, the covalent bond will break and you have the creation of the electrons and holes. Electron will move to your conduction band and holes will remain in your valence band. When electric field is applied across an intrinsic semiconductor, the current conduction take place by free electrons and holes as shown in the figure. So as you can see, the electron is moving on the left hand side and holes are moving on the right hand side. So this is how the electrical conductivity starts. The free electron are produced due to the breaking up of the covalent bond by thermal energy. At the same time, holes are created in the covalent bonds. At the same spot in the covalent bond, the holes will be created. Under the influence of the electric field, conduction takes place by both free electrons and holes. Therefore, the total current inside the semiconductor is the sum of the current due to free electrons as well as due to the holes. Now again, this is a diagram that I have taken from the previous slide. So it can be noted that the external wire is fully due to the electrons. So in the external wire, the current that you are getting is only because of the electrons. Refer this figures. Holes being the positively charged move towards the negative terminal of the supply, because holes are going to be attracted towards the negative pole. So here you have the negative poles, right? So towards this it is getting attracted. As the holes reach the terminal B, electrons enter the semiconductor crystal near the terminal and combine with the holes and thus cancel them. So here the electrons, as you can see here, the electrons are entering over here. So the moment the holes is reaching over here, the electron will come from this side and it is getting neutralized. So outside this circuit or outside this specimen, the current that you are obtaining is only because of your electron, not because of the holes. At the same time, loosely held, you see it carefully, at the same time, loosely held electrons near the positive terminal A are attracted away from their atoms to the positive terminal. So now what we are saying, some of the atoms which are very close to your positive terminal, here moment your covalent bond is breaking, the electron from here will be getting attracted by this positive terminal, right? So electron will immediately come to the positive terminal over here. This create a new holes near the positive terminal. So naturally, the moment the electron has moved from here and it has come over here, so here a positive charge is going to be created, that is a hole has been created, right? Naturally, this holes will again is getting attracted by your negative terminal and a hole slowly will reach to the terminal V. So this is what I have written over there. To find an expression for electrical conductivity, first we shall consider electron flow in the semiconductor. Let A be the area of cross section of the bar, Vd be the drift velocity of the electron, and be the number of the conduction band electrons per unit volume of the semiconductor. So what I mean over here is, firstly we are going to find out the electrical conductivity only due to the electrons, and then again we'll find out due to the holes, and then we are going to combine them. For this, what we are going to do is, let us suppose here we have taken a specimen, right? And this specimen has a cross-sectional area. This specimen has the cross-sectional area, and let us suppose this cross-sectional area is your capital A, right? So as we are giving the thermal energy and the electric field is being applied, the electron will start moving. So here electron is going to move, and therefore electron is acquiring a particular velocity, and that velocity we are calling the drift velocity. Since here we are going to find out the electrical conductivity due to the holes and electrons, so drift velocity for the electrons we are representing by VDE. So this is what I have written. VDE is the drift velocity of the your electron, right? We have suppose that we have the n number of the conduction electron per unit volume, that per unit volume that we are getting area is to be multiplied by the unit thickness. So per unit volume, the number of the electrons over this is n. So naturally this n number of the electrons are going to move, and naturally the movement of by the movement of this you are going to constitute the current. So what we can say, thus the free electrons in a volume AVDE, A is your area and VD is the drift velocity. So more with the be the area, or more be the drift velocity, more number of the electrons will be coming. So you can understand that if the velocity is more number of the electrons will be passing. If the surface area is more number of the electrons will be coming up through that. So thus the free electrons present in a volume AVDE will cross an imaginary plane assumed to be perpendicular to the bar per. So what we can say, the number of the electrons crossing the imaginary plane per second will equal to how much? N into A VDE. This is the number of the electrons per unit that is crossing that per unit cross-sectional area. So what is the current that has been constituted? So naturally you multiply this number of the electrons by the charge of the electron, and that will give you the current. So current due to the electrons, that is we are calling IE is equal to NE A VDE is your current, right? This current is of course due to your electron. So now you convert this current in terms of the current density. So J is equal to I upon A, where I is your current. So here IE I have taken because we are taking the due to the electrons, and A is the cross sectional area, right? So I equal to, we have got this NEABDE upon A. So this A and A will get cancelled. So here we are getting NEVDE. Here we can write E. So this is your drift velocity for your electron. So this is your third equation. Now according to the Ohm's law, the current density which is being represented by JE is given by sigma into E. Here sigma E I have taken because we are taking for the electron, and E is the electric field that we have applied, so that the electron is drifting in one particular direction, right? So sigma is the electrical conductivity for the electrons. So from equation 3 and 4, what do you do? Whatever the value of J you have got, you substitute in the equation 3, and then what we can say, J is equal to sigma into E. So just we have equated. So sigma E into E is equal to NE VDE. This is the value that we have got, right? Now the drift velocity produced per unit applied electric field is called the mobility of the electrons. And what will be the value of the mobility? So this definition you should remember: the drift velocity produced per unit applied electric field. Per unit applied electric field, the drift velocity which is being produced is called the mobility. If it is for the holes, then we'll call the mobility of the holes. If it is for the electron, it is the for the electrons, right? So it is the drift velocity per unit electric field. So what we can say, the drift velocity will be equal to mobility is equal to Vd upon E. So drift velocity VdE, here E is for the electron, mu E into E. This value that we can say over here, and the substitute the value of Vd in your equation number 5, and then you see what you are getting. So just we have substituted the value, and then what we are getting, sigma E is equal to Ne into mu E. This is the value of the conductivity sigma E for your electrons. So equation 7 represents the electrical conductivity due to electrons, right? Sigma is equal to Ne into mu E, where mu is your mobility, right? Mu is the mobility of the electrons. So sigma is equal to Ne. Ne is the total number of the electrons. E is the charge into mu into E. This is your total conductivity due to your electrons. Now let us find out what is the conductivity to your holes. So we can apply similarly the electrical conductivity sigma H can be obtained. So now there we have taken the total number of the charge carriers as N for the electrons. Here for the holes I am taking as the P. So let P be the number of the holes per unit volume of the material, and mu H is the mobility of the holes, and the charge on the holes is E. Naturally the charge value is the same, only it is a positive or negative, right? So what we can say, the conductivity due to the hole sigma H will equal to how much? Pe into mu H, right? So now you take the sum of that. So total conductivity will equal to conductivity due to the electrons and conductivity due to your holes, and this is what the value that we have obtained, we have written over here. Now we know in case of the intrinsic semiconductor, N is equal to P. So number of the electrons is coming equal to a number of the holes. Anyway, firstly what I have taken here, E I have taken common, so I am putting this N mu E plus P mu H. Now N and P are equal, and let us suppose that is being represented by Ni, where Ni is called the intrinsic density, right? So this equation 9 can be represented as sigma I is equal to Nie mu E plus mu H, and this will be your conductivity due to your electrons and holes both. So this is your total electrical conductivity right, in your intrinsic semiconductor. So we have seen the electrical conductivity in the intrinsic semiconductor and the Fermi energy in case of the intrinsic semiconductor. Now in the next class, we are going to take up the applications of the semiconductor in terms of your Hall effect. So there we can see how we can calculate the charge carrier density Ni that we have seen there. That usually is very difficult to calculate. If you are going to calculate it's theoretically or by the other experiment, it's a very difficult, but with the Hall effect we can very easily calculate. So next class we are going to take up the Hall's effect. Thank you very much.